Hi, my name is Arjen van der Vecht, and I'm a member of the technology team in Liberty Global. Together with Daan Weller of the University of Amsterdam, I will present our paper entitled Wi-Fi 6 Performance Measurements of 1024 QAM and Downlink OFDMA. The authors of the paper are Daan Weller, Raoul Dijksman, Jan Willem van Bloem, Kees de Laat, and me. This video has been recorded for the IEEE International Conference on Communications. I will start with a summary of our findings as well as a perspective on why these results are relevant to the customers of Liberty Global. Subsequently, Daan will provide more detail on how we obtained these results. We explored the benefits of two key features of Wi-Fi 6. The first feature is 1024 QAM, which brings a theoretical throughput increase of 25% compared to the 256 QAM modulation used in Wi-Fi 5. Using the free space path loss model, we determined that the maximum range of operation of 1024 QAM was less than 6 meters when using maximal transmit power. We don't live in free space. We live in a world that has walls. And due to the attenuation of walls, 1024 QAM should be seen as a single-room technology. For a substantial part of our customers, the Wi-Fi router is positioned in a closet near the electricity meter. This effectively means these customers will not really benefit from the 25% throughput increase. The added value of 1024 QAM will mainly be seen in Wi-Fi 6 mesh networks. The second feature that we explored is OFDMA. OFDMA is a multi-user version of OFDM. OFDMA does introduce some overhead compared to OFDM, and the gateway should decide based on the traffic if it is more efficient to use OFDMA or not. In our measurements using free mobile phones and simulating home environment traffic, less than 2% of the traffic actually used downlink OFDMA. The benefit of downlink OFDMA on latency is therefore expected to be limited unless the number of clients is substantially higher than the 3 clients we used, as would be the case in, for example, a stadium or mall. Based on the implementations that we tested, we conclude that the impact of 1024 QAM and downlink OFDMA introduced with Wi-Fi 6 will be limited for our residential customers. Other features of Wi-Fi 6, like BSS coloring, have a lot of potential and should be explored in future research. Especially the introduction of 6 GHz with Wi-Fi 6E is expected to be a huge leap forward. I will now hand over to Daan, who will explain how we obtained these results in the remainder of this video.
Thank you, Arjan. This research is focused on the performance gains of 1024 quadrature amplitude modulation and downlink orthogonal frequency division multiple access in Wi-Fi 6. For 1024 QAM, we are interested in the benefits in terms of increased throughput. For OFDMA, the benefit in terms of latency is of interest. First, I will describe the experiment setup. 2 reference boards of 2 different vendors are used in the experiments. For 802.11ax capable clients, Samsung S10 mobile telephones are used. The Rode and Schwarz signal and spectrum analyzer is used to make spectrum captures of the transmissions. IXChariot and iPerf are used to generate the traffic. To eliminate interference, all experiments are performed inside an RF-shielded room. The quadrature amplitude modulation measurements are divided in 2 parts. The first part consists of performing measurements on modulation encoding schemes 8 through 11. In the second part, spectrum captures are obtained with different attenuation levels using the spectrum analyzer. To the right, you can see the constellation diagram of a 1024 QAM transmission. Then, we calculate the average throughput for each modulation encoding scheme. In addition, the error vector magnitude is calculated using the spectrum captures. The obtained EVM values are used to calculate the maximum range of operation using the free space path loss model. The ratio of frame check sequences is calculated as well. .1024 QAM is capable of transmitting 10 bits per symbol. This is determined by taking the base 2 logarithm of the number of the constellation points. 256 QAM thus transmits 8 bits per symbol. Therefore, the increase in throughput when using 1024 QAM is expected to be 25%. The results show that this increase in throughput was achieved. We also observe that the throughput approaches the theoretical maximum for all MCS configurations. The expected 25% increase in throughput was achieved, however, with a limited range of operation. In this diagram, the obtained EVM values are plotted against the total attenuation used in the experiment. Each box plot represents a different experiment configuration for each vendor. The dashed line indicates the EVM threshold for successful transmissions, provided by the 802.11ax specification. As can be seen, with an attenuation of 55 decibels, the obtained EVM is higher than the threshold. This would indicate that the signal contains too much noise to use 1024 QAM in transmission. However, we did find that the frame check sequence passed, which indicates that the connection may still be maintained to some extent with EVMs higher than the threshold. Using linear interpolation, we calculate the attenuation at the EVM threshold. Using the free space path loss model and the calculated attenuation, we determine the maximum range of operation to be less than 6 meters. Next are the downlink OFDMA experiments. Two different measurements are made to compare the performance increase of downlink OFDMA. IEEE is used to generate the traffic using home environment profiles. 3 Samsung S10 mobile devices are used to send the traffic to. Multiple spectrum captures are made over the course of the transmission. From these captures, the resource unit allocation and the airtime saturation are determined. Our experiments show almost no OFDMA traffic when using realistic traffic profiles as defined by IEEE. In addition, the results are vendor specific, as vendor A has an OFDMA scheduler implemented, whereas vendor B did not have a scheduler. For vendor A, the number of OFDMA frames being sent is dependent on the buffer sizes, the number of clients, and the packet size. Vendor B has a binary configuration of OFDMA. When enabled, all packets will be sent as OFDMA frames. The scheduler of vendor A configured a resource unit allocation index of 16. This can be seen in the diagram to the right, by the unused middle tones in the high efficiency portion of the transmission. Due to this, 1/9 of the bandwidth is unused. The results show a slight increase of airtime saturation when OFDMA is enabled. However, as can be seen in the upper diagram, the OFDMA transmission consists of 2 parts. The second part of this transmission is the optional block acknowledgement request. These MU bar frames account for approximately 8% of the airtime saturation. Thus, if the MU bar frames are omitted from the calculation, we observe a decrease of 80% in airtime saturation. Vendor B has a fixed resource unit allocation that allows transmissions to 5 users. This means that 2 resource units are unused, resulting in unused bandwidth. Hence, a large throughput decrease was observed when enabling OFDMA. In conclusion, the expected 25% increase in throughput with 1024 QAM was achieved, although with a maximum range of operation of less than 6 meters. For downlink OFDMA, our findings show no significant impact on latency, though performance is heavily dependent on the scheduler. The number of clients, packet size, and the buffer size play an essential role in the OFDMA scheduling process. Due to this, we expect that the benefits of OFDMA are limited, unless the number of clients is substantially higher. This is the case, for example, in a stadium, train, or mall. Future work includes a range of operation experiments of 1024 QAM in practice, downlink OFDMA performance measurements with a higher number of clients, and performance measurements for uplink OFDMA transmissions. Other fields of interest are the added performance gains of BSS coloring and the addition of transmission over the 6 GHz spectrum. That concludes our presentation. Thank you for your time and attention, and if anyone has any questions, please feel free to ask us through the designated channels.